Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In this video, I'm going to talk about a dry subject. Drying, in fact. We'll look at how and why we dry pharmaceutical materials in the first place, and also discuss the process by which water is removed. I'll try and make the video more interesting than watching paint dry, although that is essentially what we're talking about. So, get yourself something wet, and let's get into it. Drying, in case you didn't already know, means the removal of water from a material or object. I suppose it also refers to the removal of any liquid, not just water. But water is the most commonly used solvent in medicines. There are many things that may need drying during pharmaceutical manufacture, solutions, suspensions and wet solids being the most common. And there are many reasons why we might want to reduce the water content. Dry materials are often easier to handle and move about than wet materials, for instance, and water can be a particularly reactive species, degrading drugs via a chemical reaction called hydrolysis. Moreover, many medicines have shelf lives of years, and having water in the product can cause all sorts of problems, from helping change polymorphic form to allowing contamination by microorganisms. So to help make medicines last as long as possible, we need to get as much water out as possible. And on that subject, I should note here that when we say dry, we don't necessarily mean zero water content. Most materials, even those we perceive to be dry, contain an appreciable amount of water. As humans, we are about 70% water, and even a wooden tabletop will have around 10 to 20% water. If we dried things completely, so they are bone dry, we would often end up with fine powders, and we don't usually want that. So we dry materials to a point where they are stable upon storage but still have suitable mechanical properties. All water is not equal, however. We also need to worry about where the water is situated in our material. Most people imagine that when a material is wet, it has water on its surface, and that is of course correct. We call that free water, or, if you'd like a more technical definition, free water is water that can exert its full vapour pressure. In other words, it is sitting on the surface of a material but not interacting with it. But water can also be found hiding more deeply within a material. For instance, it may be found in capillaries or void spaces. We call this bound water because it cannot exert its full vapour pressure. Inside cells, this is where the water is located in wood, and is why the dry tabletop I mentioned earlier still has quite a high water content, and may even be part of a crystalline structure if the material is a hydrate. I think you might imagine that the more strongly water interacts with a material, the harder it is to remove. Hence, if we spill water on a tabletop, we can remove it relatively easily. It's free water, remember? Without removing the intracellular water, which is much harder to extract and would in any case turn the tabletop to dust. How then do we dry a material? It's easy to think that we must heat it to 100 degrees centigrade because that's the temperature at which water boils. But in reality, we can remove water at much lower temperatures. If that seems surprising to you, think about what would happen if you got out of the shower and realised you didn't have a towel to hand. Would you boil yourself dry, or would you naturally dry out over a small period of time? Exactly. You would slowly dry off over time as the water evaporates off your skin. And why does evaporation occur, I hear you ask? It's because when two materials are in contact, any water present will distribute itself between the two materials until a position of equilibrium is reached. At this point, called the equilibrium moisture content, no further water will move from one material to the other. When you step out of the shower, one of the wet materials is you, and the other is the air in the room around you. Since air can accommodate quite a large amount of water, some of the water will evaporate from you into the air, raising the humidity. When equilibrium has been reached between you and the air, evaporation will stop, and any water left on you will stay on you. This is the reason you can't fully dry yourself in a very humid room, and it's also why you'll get wetter if you walk into a humid environment. Some of the water in the air condenses onto you, also to reach a point of equilibrium. Most methods of drying pharmaceutical materials work on the same principle, that water will evaporate from a wet material to a dry material until an equilibrium moisture content is reached. To dry a material then, the air around it is kept dry. This will force water to evaporate from the sample being dried. The key difference between you drying out after a shower and a drying method, however, is that a drying method will continually replace the air around the sample, keeping the moisture content of the air low. This means that an equilibrium moisture content is never reached, and forces evaporation of water from the sample to continue. Often the air is heated, because air has a greater capacity to absorb water when it's hot, and because heat helps accelerate evaporation of water from the sample. In this way, we can remove as much water from a sample as we like, and as I noted earlier, we usually stop drying before the sample reaches complete dryness. This is because we need the sample to have some water content to give it suitable mechanical properties. But it's also because most pharmaceutical products are not stored under conditions of complete dryness. The air around a product on storage will contain some moisture, and so even if we dried our material to zero water content, it will absorb water from the environment during storage to reach an equilibrium moisture content. Thus, it is a waste of time and energy to dry a material completely if it will simply absorb water later on. I should say, however, that some products are very sensitive to the presence of water, and in these cases you will find a desiccant included inside the packaging. The desiccant is there to absorb any water from the environment and keep the sample dry. So if you see a desiccant included in a product, you know it's very sensitive to water. When water is removed by evaporation, we call it convective drying. Convective drying proceeds in 4 stages, which for completeness I will describe so you have an idea of the mechanism of drying. On the screen is a graph of water content of a sample as a function of drying time. When we start drying, indicated by the red dot on the y-axis, water evaporates from the sample, and the water content is seen to reduce. In this early phase, called stage 1, the rate of water loss is linear, because water is evaporating from the surface of the sample, the free water I mentioned earlier. Eventually, however, the rate of water loss starts to slow down and becomes non-linear. The point at which this occurs is the start of stage 2 and is known as the critical moisture content. In stage 2, water still evaporates from the surface of the sample, but it arrives there from capillaries in the material. Because it takes time for water to move from capillaries to the surface, this is a rate limiting step, and it slows down the rate of water loss. In stage 3, the rate of water loss is still reducing, now because there is no water left on the surface of the material and all evaporation occurs from within capillaries directly. Eventually, once the water content of the material is in equilibrium with the surrounding atmosphere, evaporation stops, and the sample is at its equilibrium moisture content, shown by stage 4. The main methods of drying used in the pharmaceutical industry are tray drying, fluidised-bed drying, spray drying, and freeze drying. Of these, all are based on evaporation, or convective drying, except freeze drying, which is based on sublimation, and which, as you might guess from the name, does not involve heat. In chemical laboratories, microwave drying is also used, which is essentially putting the material to be dried in a microwave oven, just like you might heat up food in your kitchen. I'm not going to explain the methods of drying here. I have separate videos for each method, the links for which are in the description below. But what I will say is the choice of drying method depends on the type and amount of material to be dried. If the material is a wet solid, typically a wet granulated powder, then tray drying or fluidised bed drying are used. For small masses of material, say a few kilograms, tray drying is best, and for larger masses, up to several hundred kilograms, fluidised bed drying is used. On a commercial scale then, fluidised bed drying is the most common method of drying. If the material is a solution or suspension, then either spray drying or freeze drying are used. Of these two, spray drying is the most commonly used method for many reasons. It is quick, economical, and can run continuously, for instance. And freeze drying is really only used in special circumstances. If the material is particularly sensitive to heat, if it's a biological drug or a vaccine, for example, or if it's being formulated as a powder for injection. I'll explain the reasons for that in the video about freeze drying. So, to summarise, drying is usually achieved by surrounding your sample with dry and often hot air. This forces water to evaporate into the air as the system tries to reach a position of equilibrium. By constantly changing the air, we can force evaporation to continue drying the material. Materials are not dried to zero water content as they would usually turn into powders, but to a point where they have good mechanical properties but are stable on storage. Since there is usually water in the environment around a product, even if it were dried completely, it will re-wet upon storage to reach an equilibrium moisture content. If the product is particularly sensitive to moisture, then a desiccant will be added. If your sample is a wet solid and there's only a small amount of it, tray drying or microwave drying are used. Otherwise, fluidised bed drying is the go-to method. For solutions, spray drying is used unless the material is sensitive to heat, in which case freeze drying is used. And that is all we need to know about drying. If you want to know the specifics of how each drying method works, have a look at the videos linked below. Otherwise, please hit the like button and consider subscribing. It really helps the channel. And thank you so much for watching. I'll see you again soon.